Welcome. Today we solve LeetCode problem 1872, Stone Game 8. Alice and Bob play a stone game. Both play optimally. We must return the score difference. Alice's score minus Bob's score. We will go very slowly. Rules, examples, prefix sums, the dynamic programming idea, the short O of N code, and a full walkthrough. 2 players. Alice starts first. Alice wants to maximize the score difference. Bob wants to minimize that same difference. So this is not just get a big score. It is maximize Alice minus Bob, while Bob fights to shrink that gap. Optimal play means both always choose the best move for their goal. While there is more than one stone, a turn works like this. Choose an integer x greater than 1. Remove the leftmost x stones. Add the sum of those removed stones to your score. Then place one new stone on the left, whose value equals that same sum. The rest of the row stays. The game ends when only one stone remains. Nobody can remove 2 or more stones anymore. Picture stones. -1, 2, -3, 4, -5. Alice removes the first 4. Their sum is 2. She scores 2. She puts a stone valued 2 on the left. The board becomes 2, then -5. The removed prefix is replaced by one combined stone, and the leftover suffix stays. Example 1. Stones equal -1, 2, -3, 4, -5. Alice takes the first 4, scores 2, board becomes 2 and -5. Bob must take both remaining stones, scores 2 plus -5, which is -3. Difference, 2 minus -3 equals 5. Output is 5. Example 2. Stones equal 7, -6, 5, 10, 5, -2, -6. Alice can remove everything at once. The total sum is 13. Board becomes just 13. Bob has no move, so Bob's score stays 0. Difference 13 minus 0 equals 13. Sometimes taking all stones on the first turn is optimal. Example 3. Stones equal -10 and -12. Length is 2, so the only legal move is take both. Sum is -22. Alice scores -22. Bob never moves. Difference is -22. Alice must move even when the only sum is bad. Constraints. Length n is at least 2 and at most 100,000. Stone values can be as low as -10,000 and as high as 10,000. Because n can be 100,000, an O of n squared solution will time out. We need a linear or nearly linear idea. Smart dynamic programming, not a full game tree. Prefix sums are the key. For stones, -1, 2, -3, 4, -5, the prefixes are -1, then 1, then -2, then 2, then -3. If you remove the leftmost x stones, your score for that move is exactly the prefix sum ending at index x-1. So every legal move scores a prefix sum of length at least 2. Key insight. Putting the sum stone back does not invent a brand new unrelated game. After you take a prefix ending at index I, the new leftmost stone equals that prefix sum s of I, and the remaining stones are the original suffix after I. The merge is just packaging the prefix you already scored. Go deeper. Any later move that includes the merged stone is really extending to a later prefix of the original array. So the whole game collapses too. Players keep choosing later and later prefix endpoints. The first move must end at index 1 or later, because you need at least 2 stones. Only those prefix ends matter. Think in score difference. The current player picks a prefix sum s of I. Then the opponent plays optimally and gets some best advantage from what remains. Your net advantage is your prefix score minus the opponent's best advantage. That is why the formula looks like score minus opponent best. Dynamic programming definition. Let f of I mean the best score difference the current player can force when the leftmost merged stone already covers original indices from 0 through I. So the next move must take a longer prefix ending after I. When no move is left, that player's difference contribution is 0. The recurrence. F of I equals the maximum over every later nj greater than I of s of j minus f of j. You score prefix s of j, then the opponent faces position j and gets f of j. Alice starts with nothing merged yet, so her first choice is any j from 1 through n-1. She cannot take only the first stone alone. Naive evaluation of that maximum for every I is O of n squared. Too slow. Trick. As I moves left, the set of allowed j choices only grows. So scan from right to left and keep a running best. The compact update is f equals the max of f and s of I minus f. One backward pass after building prefixes. Algorithm steps. 1. Build prefix sums. 2. Set f to the last prefix, that is taking all stones. 3. For I from n-2 down to 1, set f to the maximum of f and s of I minus f. 4. Return f. The loop stops at 1 because the first move needs at least 2 stones, so index 0 alone is never a first move end. Code sketch. First loop, from index 1 to n-1, add the previous value into stones of I, so the array becomes prefix sums. Set f to the last prefix. Then loop I from n-2 down to 1. F equals max of f and stones of I minus f. Return f. Overwriting stones saves space. Short, linear, interview-friendly. Walkthrough of example 1. Prefixes, -1, 1, -2, 2, -3. Start f equals -3. At I equals 3. Max of -3 and 2 minus -3, which is 5. So f becomes 5. At I equals 2. Max of 5 and -2 minus 5 stays 5. At I equals 1. Max of 5 and 1 minus 5 stays 5. Answer 5. Matches the example. Why this works? Simply. Taking a prefix scores that prefix sum. The opponent then gets the best remaining difference. Your net is my prefix minus opponent best. Scanning right to left reuses the best opponent options without recomputing from scratch. Alice's answer is the best first move net among all valid prefixes. Edge cases. If n equals 2, only one move. Answer is the sum of both stones. Taking all on the first turn can be best. Then Bob scores 0 and the answer is the total sum. Negatives are allowed, so Alice might be forced into a negative score. And optimal play is not always take everything. Example 1 proves that. Common mistakes. Simulating the full game tree will time out or explode. Forgetting that x must be greater than 1. Assuming Bob is dumb instead of optimal. Confusing raw scores with the required Alice minus Bob difference. And forgetting that merges still correspond to original prefixes. Do not invent a random new indexing. Complexity. Time is O of n. One prefix pass and one backward pass. Extra space can be O of 1 if you override the stones array with prefixes, or O of n if you keep a separate prefix array. That is perfect for n equals 100,000. Takeaways. A move removes a left prefix of length at least 2, scores its sum, and puts that sum stone back. Every score is a prefix sum of the original array. The difference DP updates with f equals max of f and s of I minus f while scanning backward. Alice starts, return her best difference. Stone Game VIII is prefix sums plus optimal difference dynamic programming. You got this.